So the reason why doing a Mann Whitney test or doing the non-parametric test, according to the way that I tell you on the slides through the wizard, is because if you use the legacy way of doing it, you will get the wrong answer. This particular data set is from Porthcrawl and measures the size of periwinkles in two different locations, which if I do view and value labels, and remember you should always do this, a standard process every time you open a file, where you see a column which is labeled 1, 2, or 1 or 2 or 1, 2, 3, 4 or whatever, click on the value labels and then you'll see what's going on. I don't hugely need that on at the minute because it's useful to know that the groups are coded as 1 and 2. That's just useful for me. Right, here's the heights of the shells. So what I'm doing is I'm testing, is there a difference in the height of the shells between the two locations based on an assumption that it's easier for birds to eat, birds like seagulls to eat the periwinkles in a particular location. And also there might be an effect which is due to the tidal effect being rougher, that older varieties of that seashell might live in one location compared to the younger ones living further down the beach. There could be lots of explanations why there's a difference. So the null hypothesis is there's no difference in the heights between the two regions. The alternative is that there is a difference. The reason you're doing non-parametric is because the data is not normally distributed. Now, in general, for you, because you're not BMSs or nutritionists, you're never ever going to meet anything that's not normally distributed data. Almost all processes that you're likely to meet are going to produce things that are normally distributed. They just won't look normally distributed because your sample size is too small. Right, so what do? We do analyze, non-parametric tests. This is two independent samples. The size of the snails in one region does not affect the size of snails in the other. It's not like it's the same snail measured twice. So these are independent samples. So I click on independent samples, and this is the start page of the wizard, which has 3 tabs. It says, do you want to do everything automatically? If you know statistics and know what you're doing, you can switch that automatic function off. Now, you're beginning as statisticians, so let's leave it on. So I don't need to worry about anything else. It's going to go automatic. The next thing it wants to know is which columns within your particular data file are the ones that it needs to think about. Now, in this case, there's not a lot of choice because there's only 2 columns, but you could have a set of data which has 20, 30, 40 columns in it, and you want to pick the ones that you want to do the test in. It's not complicated, just pick the ones. So I want to test about shell height, and I have my groups is based on location. That is it. Put my subsetting variable in groups, put my outcome variable, my dependent variable, whatever, in test fields. There is another tab that you can look at which allows you to do the customization and do various things, which is more advanced. Again, we're just starting, so we don't want to do that. So you press run. That's it. Nothing complicated, it's done. Now, the problem is that when it used to work, when the old-fashioned version, so if you have SPSS 24 or 23 or 2 or whatever, you just get this particular table. So it tells you the null hypothesis is the distribution of the shell height is the same across the 2 locations. It's carried out an independent samples Mann Whitney U-test, which is what we wanted it to do. It tells you the p-value is 0.264. And it says retain the null hypothesis because it's not less than 0.05. Did everything totally automatically for you. No need to think on anything almost at all. So that's how it used to be, and I used to do the weekly assessment by asking for the p-value. Now, they've changed it. So as well as doing that nice summary table, they give you some more tables underneath. I thought, oh, this is good, because now I can ask them about the test statistic as well as the p-value. Now, you could always have found the test statistic before, and it's calculated in a particular way, which I don't really need to go into. Just let's say it's a number, and which I've written a long description, and I've actually recorded me going through the process of how you calculate those test statistics. But they're a little bit involved, and they can be calculated in a variety of different ways. There's a Mann Whitney way of doing it, and there's a Wilcoxon way of doing it. But SPSS helpfully labels the one that you want as the test statistic. So the test statistic for this particular Mann Whitney test is 106.5. Not 197.5, it's 106. All good. Right, so what everyone is doing wrong is they're going down into this table and they don't know which of these numbers to pick. Well, it's the one that says test statistic and the one that says Mann Whitney, and it's exactly the same thing. Or they're calculating it using a different method to these wizards. The other thing that people are getting wrong is what's the p-value? Well, the p-value here is 0.264. The p-value in this table, you have two choices. You've got an asymptotic one and you've got an exact one. Now, you notice that the exact one is 0.264, exactly the same as the one in the table, that being the one that I want. The asymptotic one is not 0.264. This is the wrong one. This is what happens when you assume that the distribution of the ranks is normally distributed. So as your data sets gets artificially large, it will end up being normally distributed in the U-test. Therefore, these two things will approach each other. But when it is not infinite sized, then there's a difference between the two of them. I want the one that is the same in both tables. I want the exact probability of having those ranks, which is 0.264, which is the same in both. So you see, piece of cake, nothing to worry about, no difficulties. You can't get this wrong. Yeah, that's why I have about 6 emails a day saying, I got 0 on the test. What have I done? You haven't listened to anything I said in the class. I forgot, you didn't go to the class, you just read the online lectures that are there already. So sometimes you get in a mess by not attending. Right, now I'm going to show you what happened if we used the old way of doing things, because SPSS has just really annoyed me. So if I go to Analyze and I go to Non-Parametric Test and I go to Legacy Dialogues. Now, a key thing about legacy is it means outdated, not to be used really. Why are you doing this? So for example, a legacy way of storing data is a floppy disk. You don't need to use them. You don't need to know what they are and why. So legacy dialogues, you can pick 2 independent samples. Good. So you put shell height in your test variable as you did before, you put location in, and now it asks you. Before, SPSS worked it out because it's got a wizard. Now you have to tell it. So group 1 is called 1, group 2 is called 2. That's why I said it's important to look at how they're coded in SPSS, as well as looking at the labels. Do you want to do Mann Whitney, Kolmogorov, Smirnov, Moses, Extreme, or Wolfowitz? You want to do Mann Whitney, you press OK. So it goes off and it does the ranks. It calculates the sum of the ranks for the lower shore, the sum of the ranks for the mid shore. Notice the sum of the ranks for the lower shore is 153.5, for the mid shore is 197.5. Now you've seen that 197.5 before because it's the Wilcoxon W in the new table. But the Wilcoxon W in the old table is 153.5. So what SPSS has done has moved from using the smallest sum of the ranks as the test statistic to using the largest sum of the ranks as the test statistic for the Wilcoxon. For the Mann Whitney, it's made an even more complicated pain in the neck of a calculation. If I add these two values together, I get whatever it is, and I average it. So add these two things together, 153, and so that gives me 351. So in total, I'm going to be 175.5 would be the true average. If both of these had the same amount of ranks, they'd both be 175.5 if it was equally split between the two. Now, the most extreme I can get is the different if the numbers 1 to 13 are in one and the numbers 13 to 26 are in the other group. So what the Mann Whitney does is it calculates the actual sum of the ranks, the difference between that value and the average value if it was split equally between the two, and compares it to the maximum difference you could get. Now in the original one, it calculated, so in the original one you have here, it calculated the difference between the Mann Whitney that you're actually seeing, the actual units, and the average. So the 62.5 is the difference between, actually it's not 170. It's the difference between the mean of the ranks and the highest actual rank that you get. What it's doing now is it's subtracting that 62.5 from the maximum possible difference to get this new Mann Whitney statistic, which is 106.5. It's a pain, it's completely different. So if you calculated using the legacy, you would put the test statistic as 62.5. If you calculate it using the new one, you put it as 106.5. You see the p-value is 0.264, 0.264, 0.264. There's also that 0.258, which is here in the asymptotic. But I want the 0.264. And I don't want that Mann Whitney. I want this Mann Whitney. So if you use the wizard, you get the right numbers. If you use the legacy, you get the wrong numbers. So don't use the legacy.